Hello teammates, it's Mr. Nannini coming to you with another Physics Bunker production. We're going to look at free response question practice number 7 from Friday. I'm gonna go through those this afternoon, and you can look at those solutions. Look at my comments, please. And I recommend you watch the video. I'm going to give you some tips that aren't on the solution key, and I think hitting with both of those is going to make you a stronger physics student. So let's dive in. I'm trying a different technique, so I copy pasted this so I've got more room to write and things aren't all squished in. Hopefully that makes it more useful to you. If not, let me know. So we're gonna read the question carefully. We're gonna read the whole question first, and then come back and start answering it. Right? You don't want to just answer sequentially, because you might miss something. You might miss an Easter egg somewhere that maybe you get a tip. Maybe some neurons fire. So when you're approaching these, it's an angular momentum, conservation of angular momentum. Approach them very similar to how you would for a linear momentum problem. Just like linear momentum, angular momentum is going to be conserved. Don't be concerned. Non-uniform rod, that's a distractor. As I've mentioned, the AP Physics test writers don't play. This isn't AP Lit. This isn't AP Gov. This isn't AP Lang. Nobody cares how you feel about Romeo and Juliet. They want to know, do you know your physics? And that's a distractor. Here's why you don't have to worry about that. They don't give any other detail, for one thing. Two is, if you look, the puck, strikes the rod at each place. If they don't tell you the rod is different, you just gotta assume they're the same. You wouldn't be given 3 different rods. You might see a problem with 2 different rods. I don't think you'll see 3. All right. So don't know that sometimes distractors are worked in, and they want to see if you know physics. So I already ranked these, and if you were taking this on paper, I'd recommend you do this too. I don't know it's gonna be worth your time taking out a computer to write on. So greatest, second, least. Here's why I did this. It's like a linear collision. In the first case, the puck's gonna hit the rod and bound back, right? Before and after. The momentum of the puck is going to equal the momentum of the rod minus the momentum of the ball, right? They're going in different directions, right? This is going in the negative direction. This is going in the positive direction. And it doesn't tell you which way is which. But you know up is going to be positive, probably down is going to be negative. You know they're different, so you can do that. Now I rearranged this. I solved for the angular momentum of the rod. Angular momentum of the rod is equal to the initial momentum of the puck plus the final momentum of the puck. I missed that. I meant to write P there. There you go. Right? We're going to add that to each side, solve for the momentum of the rod. It's going to have twice the momentum of the ball because it's bounding back out. So momentum is still conserved. Your net momentum is still the momentum of the puck. I hope that makes sense. This one, it's like a collision where the momentum is transferred. So the momentum of the puck becomes the momentum of the rod. This last one is like a totally inelastic collision. That's special case. Recall in collisions, elastic applies if kinetic energy is conserved. If it's not conserved, it's inelastic. And there's a special case of inelastic where they stick together, and that's what this is. And so the momentum of the puck is going to be the moment of inertia of the puck plus the rod. We're not given that, but we can kind of reason through. If we add our moments of inertia, divide both sides by that, we're going to get a much lower velocity, right? By angular momentum equals moment of inertia times angular velocity. It's good. Let's attack now. Now that's a whole long setup. This was a nice problem. We're going to sketch this graph. Teammates, we are told you're not going to have to write graphs next Thursday, but I think you're going to be asked to interpret graphs. So you may be given a series of graphs and asked which one applies to the situation. I think this is worth doing. We're going to rank angular momentum of the puck, angular momentum of the rod. I drew a little picture because we're told to look at case one. Look specifically what one you're looking at. Read critically and attack. I put a note here on collisions. Unless told, now clearly a collision doesn't happen instantaneously. Clearly the objects are in contact for some period of time. But if you are not given a period of time, you've got to make the assumptions that the period they're in contact is instantaneous. And press on from there. So let me show you what I did. I know the puck is moving in the positive direction, so I'm going to give that a positive momentum. It's moving at a constant velocity. It's got a right even by moment of inertia for a point object. Angular momentum, MVR. Mass doesn't change, velocity doesn't change. It's moving perpendicular, radius doesn't change. I'm going to give it a constant positive momentum until time c. We're told time c is when the collision happens. That's where that time c is. Let's look at the rod. The rod's stationary. The rod's stationary by angular momentum equals moment of inertia times angular velocity. If angular velocity is 0, your angular momentum must be 0 as well. After the collision, all right, collision happens at time c. The rod moves in the positive direction. So you got to be careful. It's a trap again. You got to think through what's going on. So the rod's moving the positive x direction. It's got a positive momentum. Positive linear momentum. Angular momentum. The puck goes back in the negative direction. So it's got a negative momentum. All right, so that's a trap. You can connect your lines there if it makes you feel complete. I wrote some notes here this is 2 points. Momentum is conserved. Angular momentum is conserved. Look what I've done. Your key on AP Classroom is a little different, and I did that deliberately so you can think through. I've got 1, 2, 3, 4, 5 times 3, 15 units of momentum, angular momentum. So I've got to have momentum's conserved. No external torque. 15 units of momentum. I got to have 15 units of momentum. Now you're saying, now wait a minute, Mr. Nini, this is smaller than that. I've got 2, 4, 6, 8, 10 units of negative momentum. I've got 5, 10, 15, 20, 25 units of positive angular momentum. 25 minus 10 is 15. 15 units of angular momentum. And that's all they want to see. That's all they want to see. There's no reason to torture yourself. Right? They're telling you angular momentum is angular momentum. You know angular momentum is conserved. So if you got some positive here, you got to have the same quantity there. In the absence of an external torque, angular momentum is conserved. And in this case, we are considering this all one system. There's nothing external coming in. It's good. Let's go. Let's go. Rank is rotated 2 seconds after the collision. 1 for the greatest, 2 for the next greatest, and so on. They could have written just 3 for the next greatest, I guess. If they're the same, you got to use the same number for the ranking. Good. All right, it's a trap. Has rotated 2 seconds after the collision. It's a trap to slow you down. You're told that the surface is between the rod and the surface, and the puck and the surface is frictionless. So it doesn't matter what time it is. The instant these make contact, you've got that. So that's a distractor. As identified above, 1, 2, 3. See previous page. That was my note to tell you is good. On the last part, on AP Classroom, they've got a couple sample paragraph length responses. I strongly recommend that you read these. Make them part of your Weltanschauung, your worldview on how you solve these kind of problems. And I think that's going to help. I don't think I need to rewrite those paragraphs here. I think my astute students of physics are totally capable of reading those. The key points, though. Your narrative has to correspond to the ranking. You can't play games. They're going to catch you. You can't say, "Oh, I don't know if it's is it 1, 2, 3? Is it 1, 3, 2? I'm going to write this, but I'm going to say something else here." You're not going to get your points. They're going to see right through that. Your narrative has got to support what you wrote up here. You want to just lay it out. Greater angular speed after the collisions can result in a greater angular displacement. Don't leave parts on the table. Don't leave points on the table. Right? You're asked to rank angular displacement. You got to relate that to angular speed. In collisions, angular momentum lost by the puck is gained by the rod. Easy money. Pucks change in L in case 1 is greater. We've talked about that. Explain why the rod's angular momentum final is greater in case 2 than case 3. And you're good. You get 1 point, 4 more points. Strongly recommend claim evidence reasoning. College Board, the physics people at least, have gone to this framework. Give the people what they want. Claim evidence reasoning. You'll see that on the second paragraph on AP Classroom. It's good. Leave nothing on the table. Leave nothing assumed. You know that angular speed is going to relate to angular displacement. In the absence of friction, absolutely. Don't leave it on the table. Specify that. It's good. Hot dog, teammates. Have you a great day.